Started. So welcome everyone to the October 2025 edition of Tokyo Space Cafe. So today we're very happy to have Dr. Eric Paic from the University of Tokyo. So he will be talking about Einstein's magnifying glass. So first, just a brief introduction. So after learning about the universe with various documentaries and his telescope, Eric studied astrophysics at EPFL in Switzerland. And he was introduced to various aspects of gravitational lensing during a summer internship with Dr. Frederic Courbin. And he wanted to learn more about it, so he did his master's and PhD in Dr. Courbin's group, and then he came to Tokyo to continue his research. So Eric is going to tell us all about his work. So Eric, whenever you're ready.
Yes. Hi everyone, thank you Ken for the introduction. Whoa. Yeah, so thanks for the invite, and it's a pleasure to be here to see so many astro enthusiasts and tell you a bit about my research. And so today I'll try to walk you through the different secrets of the universe that we are still trying to unlock, and how we can do this with gravitational lensing. So the story starts, as often in astrophysics, with this German guy. You might have heard of him before. So Albert Einstein discovered general relativity in 1915, and the main mind-blowing thing about it is that he discovered that gravity is not a force that attracts a thing, but rather a deformation of space-time. And if a light ray goes straight down its path, it will continue to go straight through the space, even though it's close to a mass, but the mass bends space-time, and so its path will be bent as well. And so you have this phenomenon when you have multiple light rays coming towards a mass. The observer will have the illusion that the luminous source is a different place than it actually is. And this is how the theory was demonstrated by another a British guy this time called Arthur Eddington. So what he did was to organize an expedition to these places in South America and South Africa during the 1919 total solar eclipse. And what he wanted to observe was something like this. So seeing the position of the stars before the eclipse and after in red, he wanted to demonstrate that the relativity, as Einstein described it, was actually causing this deflection. So that's what he wanted to see, and that's what he actually saw. So I don't know about you, but I cannot see a lot in this picture. Like, we can barely see the position of the stars that he was aiming for. So there are a lot of talks about how he maybe manipulated a bit the results and cherry-picked what he liked most about it to demonstrate Einstein theory. But in the end, I mean, it didn't matter because we had much more proof of general relativity after that. But the symbol was that after the World War I, an English guy would demonstrate the theory of a German guy. And so it was kind of a symbol of peace, which is why Einstein became very famous afterwards. And so now you know all you need to know to understand. This is going to be, yeah, to understand what is going on in this picture, where, yeah, press maybe once, yeah. Yeah, so you have a uniform background of galaxies, and if you put a mass anywhere on this background, you will see the background light being distorted, and so that's the gravitational lensing at its best, where you see different ways that gravitational lensing is impacting the background. So you see that there are again, yeah. So before it was a simulation, this time it's a real observation. So you see that depending on the alignment of the luminous background with the mass, so here the mass is these two big galaxies here, you have different things that can happen. So here in blue, you have two images of the same galaxy that is in the background. In red, it's also two images of one galaxy. And so that's the regime that we call strong lensing, because it's creating multiple images. And then you have in violet, in purple, what we call weak lensing, because it doesn't create multiple images, but it still distorts the apparent shape of the object in the background. So yeah, so now what kind of mystery we want to resolve with that? So let's take a step back on what we know about the universe. So it's been more than a century now that we're trying to find out how the universe evolves, what is it's made of. And so it started with Edwin Hubble when he first measured the distance to some nearby galaxies and their velocity. And he realized that the more they are away from us, the fastest they go away from us. So he created this law that we call the Hubble law, which is just a proportionality between the velocity and the distance of an object, and the proportional constant was called the Hubble constant, which we can call the current expansion rate of the universe. So that's his discovery, is that the universe was expanding. And some years after, there was these guys who took this observation a bit further away. They observed not only galaxies but supernovae, so they could go much further away. So this is indicative of more or less the distance that Hubble experiment stopped at, and they went much further away, and they saw that the linear relation doesn't hold when you try to see at longer distances. And so that they needed to include this dark energy component to explain the observations. And so now we know that if you want to know the evolution of the universe at a given time, so this h of z is the expansion of the universe at a given time, it depends on h naught, so that's the constant you already know, but also on these other parameters that are the densities of matter, radiation, and dark energy. So you don't need to understand the whole equation, but just to see that the evolution of the universe is linked mathematically to the current expansion rate of the universe, so what we experience now, and also the content of the universe, how much is there of these three ingredients. And so there was another experiment to measure that, which was the cosmic microwave background. So that's the background that you can observe, that it's the furthest away from us. It's when the universe was only 300,000 years old. So there was a telescope. First it was COBE, then now the latest one is called Planck, which observes in every direction around the night sky, the furthest away possible, to map the whole night sky in this with this background radiation, and that's what we see. So we see this is the oldest picture of the universe we can see now, and we can see that it's not perfectly homogeneous. There are some places where it's overdense, some places where it's underdense, and the location and the distribution and the intensity of these over and under densities is tightly linked to the three components that we were talking about before, so the matter and dark energy mostly. And from this we were able to measure that in the universe there is 68% of dark energy, 27% of dark matter, and what is left, less than 5% of ordinary matter. Ordinary is what we know, what we see in the night sky, so the stars, galaxies, planets, and so on. And so then we're like, okay, we know there is dark matter, but where is it? How is it distributed in the universe? And if we run a simulation, like knowing that at this epoch the universe is just a cloud of gas, basically, hot gas. What are the structures in the universe today? And so if you run a simulation with that, you end up with this kind of structure. So here every dot is a galaxy. And we can see that the galaxies are ordered like filaments. And you have like places with a lot, huge densities of matter, so of galaxies, and places with under densities, we can call them void. And so there is this parameter that we use to characterize this clumpiness of the matter, which we call sigma 8. So the higher sigma 8 is, the more clumped will be the matter, and the lower it is, the more uniformly distributed it will be. And so from CMB, we got a measurement for sigma 8 and also for all those parameters I told about before, so basically H naught. But this all relies on a cosmological model that we assume, that we call lambda CDM for dark matter, to say that it's a universe composed with dark energy and dark matter. And but to ensure that this model is reasonable and that it's not biased in any way, we need to complement it with some other measurement that would be ideally independent of the first model to see if the measurements agree, and we can call it a day and say we solved the universe. So if I'm here, obviously we didn't do that, because you can see that if you're an astrophysicist in the 2000s, so that's just the history of the measurements of H naught as a function of time, and using the two different approaches. So one is from the CMB, the other is from using a supernovae. And you can see before 2010, it was like almost they were in great agreement and everything was good. But as we improved the methods and the instruments, then a tension became to become clear between measurements from the local universe, the CMB, and the local universe. And this tension now has risen to a point where it's very highly unlikely that it's just a statistical fluke. And the same goes for the sigma 8 parameter, so the clumpiness of the matter. You can see here the measurement that we got from the CMB, and here measurements we got from other types of methods. So it's not as the tension is not as high as with the H naught parameter, but it's still present, and we need to address it. So there are two ways two possibilities we can go. So either our measurements are wrong, so all those, maybe one or many of the measurements could be biased by some effect that we are not aware of. This is still possible. Or the cosmological model that we rely on, the lambda CDM, is wrong. So of course, for a scientist, it's more exciting to say, oh, the cosmological model is wrong, and we're going to revolutionize everything like Einstein did it a century ago. But before we can claim that, we need to make sure that our measurements are really accurate. And to make that, to confirm that, either you just improve your measurements, which is already done, or you also add new methods to see if the new methods are in agreement with one or the other. And this is where lensing, gravitational lensing comes in the stage again. That's what I will present today, how the strong lensing can be used to measure H naught, and how the weak lensing can be used to measure the sigma 8, so the clumpiness. So how do you measure H naught? So if you have a strong lens system, you have multiple paths that are created for the light, and there will always be a path that is a bit longer than the other, and so this will create a time delay for the light rays that travel from the source, from the same source to the observer, to the Earth. And this guy, a Norwegian astrophysicist called Hevsdal, got an idea in '64 that if you could observe a supernovae that is lensed, so behind the foreground galaxy, then you could have, since a supernovae only lasts a few weeks, it's a very short event, you could see the first image popping, then disappearing, then the second image, then the third image, etc. And so you could determine this time delay. And this time delay would be linked to h naught, so the cosmological parameter we want to measure, and delta m, which would be the difference in mass between the path that crosses here and the path that crosses there. So historically, supernovae are quite rare to see, and strongly lensed supernovae are even rarer. So what the field started to work on was strongly lensed quasars instead of supernovae. And quasars are centers of galaxies that are intrinsically varying all the time in a chaotic manner, let's say. And they are the brightest object in the universe. So that's the first strongly lensed object that we found that was varying in time. And yeah, that's what we started to study. So in the collaboration I'm working in, which is called TD Cosmo, we try to take this to use all the discovered strongly lensed quasar and do this measurement of the time delay. We could also guess maybe the amplitude of this wave based on how deformed the background is. And so that's what is done also with weak lensing, where you have a background of galaxies that is deformed by a foreground of large-scale structures. So this time it's not, so usually the large-scale structures are much bigger than a galaxy or even a cluster of galaxies. So there are no multiple images that are created because it's not dense enough, but it will still deform slightly the shape of the galaxies. And so here, if you assume that the galaxies in the background are perfectly spherical, then when you see a slight shear, that's the effect that we call, that is applied to the image, then you can guess that there is a mass somewhere that is creating this shear. Of course, in the universe, the galaxies are not perfectly spherical, so you have to count this effect statistically. You cannot just say, oh, this one galaxy is a bit distorted, it means that there is a mass. You have to create some statistical tool to study this effect. And this is what the shear correlation function is. So for example, here it's also a galaxy cluster here that is lensing a big portion of the sky. So here, this photo is actually 1 square degree, so it's like you could put 2 full moons on every side of the picture. And every dot here is a galaxy. And you can see, okay, now there's a lot of distortion in the field, but how to quantify this distortion? We do what we try to, instead of measuring just the distortion of a single galaxy, we'll measure the correlation between the distortion of 2 different galaxies separated by a given angle. So for example, if we take this galaxy and we try to correlate it with this one, so we see it's very close, but the shapes don't match. So this will go here in the low separation and low correlation part of the graph. And as you go further away from this galaxy, you may have this one where the correlation is a bit stronger, then also this one, etc. And on the other side as well, where the correlation grows because of the central mass here. And when you take so it will grow, and at some point you will have, if you take this galaxy with the one on top here, then there will be no correlation anymore, so the function drops. So here I remove the x-axis because the scale is actually much bigger for this function than this picture. This picture, as I told you, is only 1 square degree, but in fact, to do this measurement at the scale of the universe and to have the scale of the large-scale structure, we do it on thousands of degrees. So that's the dark energy survey imprint. So it's a survey that has been going on for 3 years, and so it's already done, but they released only 3 years of data. And so here you have the imprint of what they, so that's the whole night sky, and they observed this whole portion of the sky, which means that they have millions and millions and millions of galaxies that they can do this correlation function on. And what they obtained is this. So there were 3 programs that were done separately on different telescopes. And the one I'm showing you here is this one, but there were 2 other ones that were done at different redshift. The redshift is just an indication of how far the background is from us. So the background of galaxies. So here, for the background that is closest to us, we can see that the correlation is almost flat. And as you go further away from us in distance, then you have more and more correlation. And from these measurements, they were able to have this measurement of the sigma 8, so the clumpiness of the large-scale structure, as a function of the total amount of matter in the universe. Because with lensing, with this method, you're not able to say, is this a universe with a lot of matter but with low clumpiness, or is this low matter with high clumpiness? But what you can see is here the green banana is the latest results from the dark energy survey. You can see that compared to the yellow patch here, which is the measurement from the CMB, you still have this tension that is present, and so it shows that when improving the results, we still have this tension on sigma 8. And so that justifies the need for a new telescope. And so there was 2 years ago the launch of this telescope called Euclid that has a very wide field of view that will map also millions of galaxies. And since it's in space, its measurement of the shape of the galaxy will be much, much more precise than what we can do from the ground. And so in black here you have the expected precision of the shear correlation function compared to what we had before. So these constraints are with the colored dots here, and with Euclid we will have the black dot, hopefully, if everything goes well. So you can imagine that the size of the banana here will shrink, and the question is, will it shrink further away from CMB or closer within CMB? So yeah, so we talked a lot about the content of the universe, about dark matter, but we don't know a lot about what is dark matter. So there are candidates for strange particles, or we don't know if it's diffuse or clumped or compact. And there is a candidate for this dark matter that is primordial black holes, which are black holes that would have formed when the universe was still a big ball of plasma, of gas. And so so it would be fluctuation of matter within the primordial plasma that would form these primordial black holes, and now they would be just wandering around in our galaxies or between our galaxies, and we are not able to see them because they don't emit any light, and that's where so to potentially detect them, that's where another regime of lensing enters. It's the microlensing. So microlensing is just like strong lensing. There are multiple images that are created, but the images are so close together that we cannot detect them separately. So what we can detect is actually just the magnification effect that it does on the foreground, on the background source. And so contrarily to strong lensing, where the scales are much, much bigger and everything moves super slowly, so on the scale of our lifetime, we won't see any change in the strong lensing systems. But microlensing happens much faster, like within a few years or even months. So we can observe this if we observe always the same star. And that's what was done here with this. So this is from a program called OGLE, which monitors a lot of stars in nearby galaxies. And the idea is that we know a star has a constant luminosity, right? So if it's just a flat line, it means that nothing is going on. But if you have, at some point, some magnification and demagnification, it might mean that there is microlensing. And that's what happened in this star here. You see that in blue, this is a ground telescope that was observing the star every night for like 1 year and a half. And after 1 year and a half, we started to see a peak. And so then they asked for HST observation of this, and that's what they got. They caught the demagnification of the star, which you can see here in the 4 different epochs. And by fitting this curve, they were able to find that it could be a black hole that is around 3 times the mass of our sun. So fortunately or unfortunately, it's compatible with a standard black hole made from a star, so it's likely not a primordial black hole. But the fact of discovering or not discovering this type of event tells us more about the abundance and the mass that this primordial black hole could have. So you have here the range of mass in abscissa and the range of abundance that primordial black hole could represent. And you can see that all the colored parts are the parts that we know primordial black holes are not expected to be. So it means that we don't expect the whole dark matter to be black holes that are the same mass as the sun, so it will be here. So we still have all this space to explore. So for now we didn't detect any, but it might come anytime. And this could come with the next generation of telescopes. And so, yeah, to sum up on that, I hope I convinced you that gravitational lensing is a very nice tool. It can help us to unveil a lot of questions. I took only 3 types of applications for the 3 main regimes of lensing, but there are much more. And yeah, the future is bright for astronomy in general and also for lensing, because these 3 telescopes here are very much complementary. Euclid is, so as I was saying, a wide field view. It will make a map of the sky, so find a lot of more lensing systems. LSST is a telescope that will observe the whole night sky every 3 days, so it will help us also measure the H0 constant. And JWST is really the super high resolution telescope that will help us have detailed observation of any system. So yeah, thanks, and I'll be happy to answer any question.